Hi, we're going to finish up chapter 5. And now you can meet this guy here is 2 pi. He walks in circles all the time. And this guy here is one that was so feral I couldn't pet him when I met him. And now he won't leave my side. His name is Grizzly. So anyway, I like recording lectures at home because I have lots of friends at home. Okay, so we're going to continue and talk about molecular orbital theory, if I can get 2 pi to move off my table. Let me start the show. So molecular orbital theory is the most accurate theory. So rather than like valence bond theory, take orbitals, atomic orbitals, and see how they overlap, molecular orbital theory calculates orbitals for the whole molecule. So it's something you have to do on a computer. We're going to do a lab in class where we use the computer to actually create some of these molecular orbital diagrams. So our learning outcomes, we want to outline the basic quantum mechanical approach to deriving molecular orbitals. And you only use atomic orbitals as starting points for the molecular orbitals. So it's really an artifact of the fact that we can't solve things exactly. So it gets a little confusing. I like to not focus so much on the atomic orbitals that contribute. But it's a popular thing to focus on in a Gen Chem text. So we're going to describe the traits of bonding and anti-bonding orbitals. We're going to calculate bond orbitals. We're going to write molecular electron configurations, and then we're going to relate electron configurations to the molecule stabilities and the magnetic properties. So if a molecule is paramagnetic, which means it has unpaired electrons, it would be attracted to a magnetic field. And this is just a picture that could show you how that is measured. So if you have a magnetic field on and off, and you measure the mass of a sample, it's going to have a greater mass if it's being pulled towards the magnet than if otherwise. So there you can actually measure the property of how many unpaired electrons a sample has in this way. This is just showing you that idea that you can have constructive and destructive interference. So we talked about this back in our original chapter where we talked about atomic orbitals. So if you have peaks and peaks lined up, so both of your functions are positive, you get a maximum overlap in a bigger function. Whereas if you're adding together two functions where a peak and a valley are in the same place, then they're going to cancel each other out when you add those two together, and you're going to get destructive interference. So when we think about molecular orbitals, that will be important for especially when we understand anti-bonding orbitals. So this just shows you, you start with some atomic orbitals. And really the reason you start, as I said, with atomic orbitals is because you need to create a function that's in the same space as those. So that may be hard to understand, but I just like to think about going from the far left to the far right. So if we had individual atoms, we'd have s atomic orbitals, but when we calculate the molecular orbitals, we get where the two functions are added together, a bonding orbital at the bottom. And at the top, we get something called an anti-bonding orbital. So if we added it together by changing the sign on one of the s orbitals, so one was blue and one was red, we'd get this anti-bonding orbital where one lobe, they should have one lobe red and one lobe blue. So let's see if they do on the next ones. But on the upper one, the reason there's a lobe is because there was destructive interference when you created that molecular orbital. Yeah, so now they're showing you the colors. This should have had color. So if you add together two p orbitals, you get a huge lobe in the middle where you call that a sigma bond, because that's the high probability of finding the electrons in a circular cross section between the bond axis. Whereas if you add together two p orbitals where you flip the sign, so a blue is overlapping with a red, remember blue means the sign of that function is positive, everywhere on the red lobe, it means that that same function is negative. And when you add those together, you get a region in between where you have 0 probability because of destructive interference. And so you would get what's called a sigma star. You'd get a anti-bonding orbital. You don't have glue between the nuclei. You have a region of 0 probability. Same thing is true for pi bonds. You can think of them as the overlap on the bottom. If you have the signs in the same direction, then you're going to get a pi bonding. Whereas if you flip one, you're going to get a pi anti-bonding because the red and the blue will overlap destructively. And so you'll have a nodal plane between the nuclei, which means you'll have a region between the nuclei where there's 0 probability of finding electrons, which means there just isn't any glue. So it's anti-bonding. It's not helping to hold the molecule together. Whereas in the bottom picture, even though the electron density, the red and the blue lobe on the far right lower part are above and below, they're still between the nuclei. So you still have probability of finding the electrons between the nuclei. And so that's a pi bond. It's a bonding orbital. This is just showing you other ways to add together. So if you add blues and blues, you're going to get a sigma bonding orbital. If you tried to add 2 pi orbitals that are perpendicular to each other, on the top, the red would cancel with the blue orbital it's overlapping with, and on the bottom, it would constructively interfere, and so those cancel each other out. So in the middle, you'd get no bonding, and C, you would get anti-bonding because the red and the blue are going to create a node between the nuclei. So this is just a picture of that anti-bonding. It's going to be a sigma anti-bonding because if you cut it across the bond axis, you get a circular cross section, but there's a node in between the 2 nuclei. There's a region of 0 probability of finding the electrons. And so that's not going to help hold the molecule together. It'll help pull it apart. And that's showing you that node by putting the dashed line in. So Walter Kohn created something called density functional theory, which is a way to calculate these molecular orbitals. This math is extremely intense, takes tons of computer time. You can't do it exactly, so you have to find approximate ways to do it, which is my area of research. I do theoretical and computational chemistry, where I like to think about the math behind these processes and then thinking about how to make the computer algorithms more efficient so you can calculate bigger molecules. So if you're trying to do molecular orbitals for something like a huge protein in biochemistry, it might take you days for your computer, even a supercomputer, to calculate the molecular orbitals. So Kohn developed a theory called density functional theorem, which won him the Nobel Prize. And this is just showing you a picture of a protease, which is a enzyme, and the picture in the middle is showing you all the bonds, and the ribbons represent a way that you often visualize these molecules, but they're huge, and so they take tons of computer time to calculate molecular orbitals. Whereas if we have something small, like beryllium diatomic with a plus, so a cation of 2 beryllium atoms, we have 3 electrons, and so in the valence shell. So the lowest energy orbital is a sigma created from the 2s orbitals. And in my opinion, I leave off that 2s. You can put it on if you want. And then the upper orbital would be a sigma star where you added 1 and subtracted the others so that their signs were different. So we're going to actually calculate these molecular orbitals. So you'll see how I knew one was lower in energy than the other. And that's simply because of what the computer gave you. But once you have the molecular orbitals, so the sigma 2s, the sigma star 2s, then you fill them just like atomic orbitals. Each orbital can take 2 electrons, Once you put 2 electrons in an orbital, it's full and their spins have to be paired, just like atomic orbitals. You'd also follow Hund's rule, which we'll look at here in a second. So this is diatomic hydrogen. So when you form the hydrogen molecule, you form it with a sigma bonding orbital. And this represents helium. And we're going to see in a second when we calculate the bond order of this, the ability for the sigma bonding electrons to hold it together is canceled by the sigma star. And that's why helium is not a stable molecule, but we'll calculate the bond order to show that. This just shows how the molecular orbitals change. So you don't always know the order. And that's why we're going to calculate the order with a computer. So we see how this, how we know this. And this just shows you that pattern of where it flips to the fact that the sigma is lower in energy than the pi. But once again, we're going to actually calculate these so we understand better how I would know this. I'd know this because I calculated them with a computer. This is just kind of thrown in here, so I'm going to skip it actually. Talks about metals, and metals basically you have atoms and then you have huge delocalized orbitals. That's why they conduct electricity. So electrons can move in that delocalized orbital throughout the whole metal structure. And this just shows you that if the purple orbital is the highest occupied orbital, if it can jump up easily to a conducting orbital, one that's delocalized over the whole molecule, it's going to be a conductor. So on the far right, you have a conductor. In the middle, the gap is the white part in the middle is the difference in energy. Slightly bigger, it's a semiconductor. And then if the gap is really big, it's an insulator. So this just shows you O2 and that question we started this chapter with, that oxygen actually has 2 unpaired electrons. And so when we create the molecular orbital diagram for it, we have 2, 4, 6, 8, 10, 11, 12 electrons in the valence shell. Hund's rule tells us when we need to put in these last 2 electrons into those pi star bonds, our orbitals, then Hund's rule says always put them into different orbitals if they have the same energy and don't pair their spins. So this shows you that we can understand the fact that oxygen is paramagnetic, which means it has unpaired electrons and would be attracted to a magnet. From molecular orbital theory, something we couldn't have understood from Lewis or from valence bond. So when we look at this, it's extremely hard to even visualize molecular orbitals for big molecules. So yeah, these are just exercises out of the back of the book, and they're actually not wanting you to do anything with molecular orbitals. So we'll look at these exercises in class. And that is the entire chapter. So as I said, we'll do a lot more with molecular orbitals in class by actually calculating with a computer.